Today we are going to study about Introduction to Power Electronics. Why do we need to know about this power electronics? We'll have a brief idea about why do we need to study about this electronics and basically power electronics. So when it comes to power electronics, three terms are associated. One is your power. Second comes electronics. And the third comes control. When we want to know about power, that means what? We need to know about what is generation of power, then transmission of power, then distribution of power, these three things we need to know about power. And when it comes to electronics, second part, that is we need to know about solid state devices. Then where to use these devices, the circuits. So we need to know about the electronic circuits. Then when these electronic circuits they process, when they work, they give some signals, that is signal process. These solid state devices, this signal process, these all are having like these components we need to know in a very clear manner. So when we come to control, for these devices, for each and every device, we need to know about their characteristics. So there are like two characteristics that we must know. One is your static devices. Static, steady state, characteristic. Another one is your dynamic characteristics. These two characteristics we always need to know about these devices, how they function, what is the different characteristics of each and every devices. So in general, when we say generation, I am just rubbing it, when we say generation of the power is needed. So we need to generate it, then we need to transmit it, then we use in the load side or we use it at output. So in general basis, when we say generally, in general transmission, if we say in general process, we can say in the general process, what happens? We need some fuel or sources, or we can say some sources. Those sources may be renewable, they may be non-renewable, whatever. We need a fuel. When this fuel burns or when we use this fuel, it gives us energy. This energy is then transmitted and in various processes, it goes through various processes and then it is transmitted, then we get in the load, that is in the output section. Here what happens? In general, suppose for example we are taking 100 kilowatt energy. If I have 100 kilowatt energy we get from burning this particular fuel. Now what happens? From this 100 kilowatt of energy, only 65% of this energy is this 65% What happens to this 65%? The 65% of this energy is lost and only 35% is transmitted. For example, I am saying this is like I am taking a reference of like back to 5 to 6 years. This is a reference. 35% is transmitted, and in this transmission process we go from like mechanical to electrical conversion. From this electrical conversion we go to the load. So these are the process. This 35%, when it is transmitted, here also we get some losses. We also bear some losses, and only, for example, 16% we get it as our output or load. Only 16% we are getting. That means what? Over from in this transmission period, 84% of the energy, 84% from this 100%, 84% is a loss. Now the function of this power electronics or the study of this power electronics comes into play. We are trying to reduce this 84% of loss. This is a huge loss. Even if we if we can save a fraction of energy also, if we like 1% or 2% of energy, if it is then also saved, it's a big deal then. Here comes the play of this power electronics. We are using some electronic devices, some power electronics devices, so as to reduce this loss, this particular loss. We can use these particular devices in places somewhere like this, in the mechanical part, in the electrical part, or in the load section. Before this load part, we can use these things. We can use the devices. So some of the devices, when we say these electronic devices, we said about the electronic devices, the solid state device, those may be like power diode, SCR, the thyristor family things, the triac, the diac, these things. Where are the applications? We can use it for rectification, for amplification, for conversion of AC to DC, from DC to DC, or like DC to AC. These conversions, rectifications, as I said. So these are the applications. For freewheeling, these are the applications, and these are very important for your further studies. So let's study about a very common device. Previous classes you have learnt about, you have heard about your signal diode, and today we will study about the power diode. Now what is the difference between this signal diode and power diode? In analog you must have studied about signal diode. When we say in general a diode means what? It refers to signal diode. When we say power diode, there is some structural difference in this power diode. When we come to signal diode, the symbolic representation is same. Symbolic representation is same for both the diodes. But in constructional point, when we say to the structural thing, then we come like this is P, this is N, P, N. There is a junction, two terminals are connected, anode, and there is a cathode. This is the junction, that is J1. Suppose this is J1, I am naming it. This junction is the depletion layer. And in this case, when we study about the structural thing, here what we have, this makes a big difference. Here we have same N and P, but they are like the dopings are changed over here. Now what happens? We have a substrate, that is N plus layer. Substrate means what? What is this substrate? Substrate means upon which, or it's a base upon which something grows. Now what is that something which is growing? That is N minus layer. N plus means, this plus means heavily doped. So we can like signify it as heavily doped N layer. And what happens here? This is lightly doped N layer. Upon this N layer, what happens? We insert a P plus layer, that is heavily doped P layer. This is lightly doped, heavily doped, and again this one is heavily doped. Fine. Now I am just erasing these things. Okay. Now we have two terminals again. One is your anode. Anode is connected to the P plus layer. This is anode. And I am erasing this too, because we'll study about the whole constructional details. Okay. Now in this outer P plus layer, we are connecting the cathode, or K or C, whatever you can give the name. Now where is the junction? This is the junction. This is the junction. This is the depletion layer. Now this region, this N minus region, gives the drift region, or this is the depletion region. This gives the drift region. We say it drift region. Now when we go for the biasing thing, we are having, like for biasing, I am giving an example like, okay, I am trying to make it a very simplified, in a very simplified manner. This is P plus layer, we are having N minus layer, and this is N plus layer. Here is the anode and here is the cathode. Fine. Now what happens? What this drift region does, we will get to know now. What happens when we say this is P plus layer? That means these are heavily doped. These are heavily doped positive charges. That means more amount of positive charges are present over here. N minus layer means less amount of negative charges are present. And N plus layer means a large amount of, or heavy amount of N, or we can say electrons are present over here. Now when we give it, when we connect it to a battery with a forward bias. So when we say it's a forward bias, this is a voltage source that we are trying to give, and when we say it as like forward biasing, this positive terminal is now connected to the anode and the negative terminal is now connected to the cathode. Fine. So the current flows like this, in this manner, from high potential to lower potential. Now when we say power diode means we want fast, like very fast forward conduction. Forward conduction must be fast. This is the term that we need. For conduction of this fast, that means current must move fast. That means when we see current is moving fast, that means what? We want low resistance. Okay. So now we'll see what is coming into play.